Solving differential equations numerically with ND-solve. That's what I'm going to cover. And ND-solve, which we can write this way, right? ND-solve, yeah. No, with the capitals S, ND-solve. It can solve ODs, PDs, and DDs, right? When using that function, we need to specify initial condition, boundary conditions, etc. Let's just start with a simple example, and instead of ND-solve, we'll use ND-solve value, so we get the value right away, and it's easy to work with it. And we can have y prime of x, that's the first derivative, x squared times sine of x. No, square bracket sine of x. We can have y1 equals 1. Then we can have, we solve for the function y, and then we say x is from 0 to 10, right? We get this interpolating function, and the interpolating function, so interpolation is when you have a bunch of points and you draw a smooth graph over them. An interpolating function is practically storing that smooth graph mathematically or in an object, so to say, in a smart way. And then we can reuse it later on. So that's what the interpolating function is. And to use the interpolating function, all you have to do is to say n solution, immediate set, and then you can just say n solution 100, or let's just say 2, and we get the value. And as you can see, if we do 11, it's out of range. The domain of the whole interpolating function is from 0 to 10, which means we can't go beyond 10 and 0. We can also graph the n solution function with x being from 0 to 10. Yeah, just like that. With x being from 0 to 10. We can also integrate it. Integrate the whole thing and solution as well. And we use x, and x can be from 0 to 10. As a result, we get the area underneath, right? We can visualize it by saying fill in axis, and we get this area underneath. Next, of course, is system of solutions. How can we solve a system of solutions? We sure can. And the solve value, then we can say x squared or x prime of t minus 4x of t plus y double prime of t equals to t squared of 2. Then we can say, now we can specify the second equation, which can be x prime of t as well. Then we can say plus 2xt, x of t, plus 2y prime of t equals to 0, x0 equals to 0. And now I'm specifying the initial conditions, right? X0 equals 0, x1 equals 1, and we can say y0 equals 0. We have all these initial conditions. Then we need to specify what we're solving for. We're solving for x of t and y of t. And then we specify the range for t, which I'll say is from 0 to 5. Okay, let me just see what went wrong. And we have this practically. Then we have x of t minus 4xt plus y double prime of t squared over 2 x of t plus x times t. And no, wait, made an error there. Now another thing, of course, is that you see how t is practically, yeah, we didn't practically specify something somewhere. Let's just go over it slowly. Y of t, t05. I don't think this is, no, this has to be outside. Yeah, now we get it. And so we specified the system of equations. That is the first question, that is the first equation, second equation. Then we have the initial conditions. Then we solve in terms of this array, which is we solve in terms of x of t and y of t, and this is exactly what we get. And we solve for the domain of 0 to 5. Now, given that we have a single variable, two functions, how do we plot that? And to plot that, we use parametric plot, system of solution, and we can say t is from 0 to 5, just like the boundaries were specified. Then we get this beautiful graph. Now, how about the partial differential equations, right? Finally, some partial differential equations. And let's say we have a partial differential equation of this form right here, and we'd like to solve it. All we have to do is say PD solution. Let's assign it that way. Just like before, we're using the solve value. And now we just need to specify the expression itself, initial condition and two boundary conditions. And let's say d u tx, that is the first derivative in terms of t, and d u tx, that is the second derivative in terms of x. And then we just need to specify the initial conditions. That is, we can have an initial condition of 0, x being equal to 0. Then we can say u t0, and it equals to sine of t, that's the boundary condition for x0. And another condition, boundary condition, is for t5, right? All these are just example expressions, example equations, right? So next we need to solve it for the t, for the u function that takes in t and x. And then we just define the t to be from 0 to 20. And we define the x to be from 0 to 5. We get this interpolating function, which we can use to plot it, right? We can just plot the whole thing. We can say t is 0 to 20 and x is from 0 to 5. Then we can say plot range all, so nothing gets cut off, and color function deep sea colors. And we get this beautiful graph of the PD we have. Just marvelous. I love the way it looks. We can also use it directly, that is PD solution, right? And we can say 1 and 1. The first is t, the next one is x. And we get that, right? So, and that's practically it.